Okay, so today we're going to look at some applications of differentiation of exponential functions, and we're going to revisit the work that we've done in calculus previously. To be able to sketch this curve, we're going to think about things like where the function's increasing or decreasing by looking at the derivative. We're going to find stationary points by solving the first derivative equal to 0. We're going to look at the concavity by exploring the second derivative, find points of inflection by solving the second derivative equal to 0, and we might also look at some applications where we're finding tangents and normals to the curve. So let's start with finding the domain of this function. So we're focusing on this function here, y equals x times e to the negative x. And when we're thinking about the domain, we're thinking, are there any restrictions on the value for x that we can substitute in here? So we can substitute in any value for x that is negative. There's no restriction on substituting that. There's no restriction on substituting in x equals 0. We could do that. And we can substitute in any positive value for x. So for this function here, our domain is all real x. Okay, so we need to then test, is this function an odd or an even function or neither? So to do that, let's start by finding f of negative x. When we substitute negative x in place of x, we end up with negative x times e to the negative x, which is negative x times e to the power of positive x. Now, if we were then to, obviously this is not equal to f of positive x, it's not equal to our original function, so therefore it can't be an even function. Now, to test if it's an odd function, remember it must be equal to negative f of x. So if we put a negative sign in front of this function here, x times e to the negative x, you can see that these are not equal results. So therefore, this function is neither odd or even. Okay, now let's find if there are any zeros and then examine the sign of the function. So that means we want to solve x e to the negative x equal 0. And we've got a product here of x times this exponential. And we know that there are never any times when the exponential function is equal to 0. So the only result that will give us a final result of 0 from this product is when x is equal to 0. Now, when x equals 0, let's look at the sign. What's happening around that value for x? And we're going to look at this table of signs. So let's take 0, let's take negative 1, and let's take positive 1. What's happening to the left of 0? So we know this is 0 here. If we substitute in negative 1 into here, we've got negative 1 times e to the negative 1 gives us positive 1. So we've got our y value is negative 1 times e to the positive 1. And obviously, this is going to give us a negative result. And then if we substitute in positive 1 here, we've got 1 times e to the negative 1. Well, e to the negative 1 is just 1 over e. So this is going to give us a positive result. So we know that this function goes below the x-axis to the left of 0 and above the x-axis to the right of 0. So this table of signs is going to give us some useful information when we come to sketch it later. Okay, examine the behaviour as x is approaching positive infinity and as x is approaching negative infinity. So as the values for x become very large here, we know that e to the negative x, as x is approaching infinity, e to the negative x, well, when we've got a very large number, that's a negative index, we know that this is going to be approaching 0. That's going to get really small. So when we multiply x by a really small number, we know that then x times e to the negative x, as x is becoming large, that's going to approach 0. It's going to get much smaller. And what about as x is approaching negative infinity? Let's think about that. So then we've got, let's just take out this exponential here. If we've got e to a very small number in an infinite, a negative direction, this is actually going to be equivalent to e to a very large positive number. But then we remember we need to consider when this is being multiplied by x times e to the negative x, what's that going to approach? Well, this is going to approach here a very large number, but if we're multiplying it by a very large number that is negative, then this is actually going to approach negative infinity. Okay, it's going to, this whole function here is going to approach a very large negative number. Now we want to find any stationary points and then examine their nature. So to do that, we're going to solve the first derivative equal to 0. So let's find our first derivative, and we've got two functions multiplying together, so that means we need to apply the product rule. So u is equal to x, and u dash is going to be 1, and then we'll call this second part of that product v, which is e to the negative x, and v dash is going to be the derivative of that, which is negative e to the negative x. Okay, now let's apply the product rule, which is y dash equals u dash v plus v dash u. So our derivative is u dash, which is 1, times v, which is e to the negative x, plus v dash, which is negative e to the negative x, times u, which is x. So y dash equals, let's take out this common factor of e to the negative x, e to the negative x, and then in brackets now we're going to have 1 minus x. Okay, now if we're solving this equal to 0, when e to the negative x times 1 minus x is equal to 0, we've got this product multiplying together to give us 0, so either this must be 0 or this must be equal to 0 to get a final result of 0. Now we know that an exponential doesn't cross over the x-axis, so there is no solution to e to the negative x equals 0. So our solution must be when x equals 1. Okay, and we need to find our y value for this stationary point and then test its nature. So when x equals 1, y is equal to, and we substitute that back into our original function, 1 times e to the negative 1. So y is simply 1 over e, or e to the negative 1. Now let's test this. So we can test by a table, or you could test using the second derivative. So let's have a look. When x and y dash, when x equals 1, and then we'll substitute. Okay, if we substitute x equals 0 into our first derivative, you can see when we substitute it in here, we end up with e to the power of 0, which is 1. Okay, and that gives us a positive result, which is increasing. We know this result here is 0, and then when we substitute 2 in here, e to the negative 2, e to the negative 2 times 1 minus 2, which is negative 1. So we can see negative 1 times e to the power of negative 2 is going to give us a negative result. So we end up with, in this case, therefore, the stationary point at our coordinate 1, 1 on E is maximum. Okay, now let's find any possible points of inflection, and we need to find our second derivative. So our second derivative is we need to differentiate this again. Here's our first derivative. We can tidy this up a little bit and rewrite it. Or we can use the product rule from here and apply the second derivative. We'll do that. So to find our second derivative and solve it equal to 0 is how we're going to find our points of inflection. Now let's go back to here and we'll apply the product rule. So our value for u is e to the negative x. So u dash is negative e to the negative x. And v is 1 minus x. So v dash is our derivative of this, negative 1. Therefore, y dash, or y double dash in this case, is u dash v plus v dash u. And u dash is negative e to the negative x times v, which is 1 minus x, plus v dash, which is negative 1, times u, which is e to the negative x. Okay, let's expand it all out and see if we can collect some like terms here. So we've got negative e to the negative x plus x e to the negative x, and then minus another e to the negative x here. So we've got a negative e to the negative x and another negative e to the negative x. That'll give us negative 2 e to the negative x plus x e to the negative x. Now let's take out a common factor of e to the negative x, and then we've got negative 2 plus x. Now hopefully we remember that when we're multiplying two terms together to solve equal to 0, this is not going to give us any solution, but our solution will be when x equals negative 2. So when we solve e to the negative x equals 0, we end up with x equals 2 is our possible point of inflection. Now we need to find our corresponding y value and then test that there's a change in concavity around this